So let's talk about energy. So here's the deal, like on number 14. What you're going to see is that a whole bunch of things can become equal to each other. So work can equal a change in energy, and that energy could be a change in kinetic energy, it could be a change in rotational kinetic energy, it could be a change in the potential energy stored in the spring. And work also equals force times distance, assuming that it's the same force acting over the same distance. So that's typically what happens like when you're speeding up a train or hitting the brakes on the train or something like that. So basically what's happening on number 14, if you were to look at like a kinetic energy versus time graph, okay? So what's the initial kinetic energy of the train? Zero. So at some point later, that train's going to have a certain amount of kinetic energy. And that kinetic energy, oddly enough, is going to change. It's going to go from 0 to some value, right? So you're going to go from 0 up to, and if your first answer is wrong on number 14, everything else is going to be wrong. So your answer to 14A should be a not so good GPA times 10 to the 8th. Okay? Now, because you had the force and you had the distance. So then on B, it asks you to calculate the change in the kinetic energy. Well, work equals the change in the kinetic energy. So your answer to B is the exact same as your answer to A is, because they're the exact same thing. Then on C, it asks you to find the final kinetic energy of the train. Well, change in kinetic energy is K minus K naught. Well, what's the initial kinetic energy of the train? 0. So all three of your answers on the first three answers on 14 are all the same value. Okay? You don't have to calculate anything. It's just work equals change in kinetic energy, and that's K minus K naught. Okay? That's it. So then we're basically going to speed the train up, and then we're going to slow the train down. Okay? Then we're going to make it stop. So what's the final kinetic energy of the train going to be? 0. Okay, so basically we went from something times 10 to the 8th joules while we're speeding up, and then we're going to go back to 0. Okay, that's it. Do not make this complicated. On number 13, where you calculate the kinetic energy of that tennis ball, that should be between 150 and 200 joules. On number 15, where you're finding that distance, that should be in the mid-60s. And every answer on number 16 should be something times 10 to the 5th. Yes.
Can we go over number 8?
Is this cars?
Yeah, because I was like confused because I was like, oh, mass, as larger mass will have the smaller velocity, right? But then it has a big, smaller acceleration.
Hold on. You're making this complicated.
Okay. Yeah.
So you got a small carrot car, and you have a big carrot car, right?
Yes.
What do they have in common? No?
Yeah.
Bigger idea. What do they have
Initial
in common?
velocity, or kinetic energy in its initial?
They have the same kinetic energy, right?
Oh.
They have the same kinetic energy. So that means the small car is
They
moving
do?
faster, and the big car is moving slower, right? They have the same kinetic energy. Pick a number. Let's say it's 100 joules, right? So they both have the same amount of kinetic energy, okay? All right. It's okay. No one heard that. Are they both going to have the same final kinetic energy?
Yes.
Yes.
Yeah.
Are they both going to go through the same change in the kinetic energy?
Yes. Yeah.
Yeah.
So they have the same work, and if they have the same force, the distance must be
Same distance?
Winner, winner, chicken dinner.
That doesn't make sense.
We have to write all that.
They don't have the same acceleration.
Oh, but how do they have the same force? Because they have different. Oh, yeah.
That's a good question.
Okay.
Yeah. Is that yeah, the international sign for, okay, now I get it?
Yeah, I think so.
Okay. Yeah.
My bad. Okay. Ella also has a question,
Okay.
but I also have that question.
What's the question?
Oh, actually, I don't have that question. She can ask that, but it's 3.
Which one?
No,
She wants
Can
She
it
wants
have
you to
potential
explain
and
it.
kinetic energy at
playing the
same
ball
time?
throwing up. Yeah.
yes. I know it's yes. But I
Okay,
can't
look.
put words on a paper.
I throw the ball up in the air. Does it have kinetic energy?
Yes, because
Why?
it's moving.
Because it's moving. Does it have potential energy?
Yes, because it's coming back down.
Or it's just above the ground?
Oh, I can just say that. Okay.
Because UG equals mgh. So the only way it can only have kinetic energy is if I roll the ball along the floor. Okay? If I roll it along the floor, then it only has kinetic energy.
Okay.
If I throw it in the air, then it has potential energy and kinetic energy.
Okay.
Okay? Does that help you with the words on the page?
Yep.
Okay. I'm all about helping you with the words on the page.
What was that
I also
equation you just
have
said?
another one.
Huh?
What was that equation you just said for that one? It was like that.
What? He said no equation. He just. What are
UG
you talking
equals
about?
mgh. So as long as it has a height, it has and as long as it has a velocity,
Can we get this one for
it
the
has kinetic energy.
name? Why didn't you tell me anything about this?
No, I did tell you about
Wait,
it.
they
I
stopped at
literally
the
said.
same distance.
Okay, did you not get the black shirt memo?
This is the only day I'm not wearing black. Well, I'm wearing black pants.
Oh, okay. I'm going, that looks awfully green. I might be way off.
She said it's the only
They
day
should
I'm
not.
not
Energy, so they're the same.
Oh, I thought you said
They
the only
stop the
day
same
I'm
distance.
wearing black, and I'm going,
No.
one of us has some really jacked up photons. I don't know who, but one of us has some jacked up photons. Okay, anything else? Going once? Going twice? So. What?
Kevin.
JD, is that guy in your encore? Jason Derulo?
All right, so here's the next big topic, which is going to form the basis of like the next 3
Did I
lessons.
crack my calculator?
And that's the idea that energy has to be conserved. So you can talk about these 4 different types of energy. You can have translational kinetic energy. Like if I take this calculator and make it move, okay? So I can have translational kinetic energy. I can have rotational kinetic energy if I just make the bicycle wheel spin. I can have translational and rotational if I make the bicycle wheel spin and move down the road. So it's possible to have both at the same time, KT and KR. I can have gravitational potential energy as long as something is above the ground. And I can have us, which is energy stored in the spring, okay? And we'll get into energy stored in the spring tomorrow, okay? So, but those are going to be the 4 primary types of energy. So what we're, for now, going to assume is that there's actually a 5th one, and that's the dissipation of energy into thermal energy, okay? That's always there, but we're just going to leave that out for now. Just because it's just like when I drop something, we assume that the acceleration due to gravity is 9.8 meters per second squared. And we leave out friction, okay? We assume that there is no friction, it's falling in a vacuum, okay? In reality, that isn't true. In reality, you're always going to be losing some energy to thermal energy, okay? It's going to generate some heat as it moves through. This is why that pendulum doesn't keep swinging back and forth all the time. Or this is why a drop ball doesn't keep bouncing up and down all the time. But here's the basic idea. Just like with momentum, the sum of the momentums before has to equal the sum of the momentums after. The same thing is true of energy. But the problem with energy is that it has all these different types of forms, okay? You can have UG, you can have us, you can have rotational, you can have translational. So momentum is a one-trick pony. It's a good trick, okay? But it's just momentum. Energy is much more complicated because you can have all the different types of forms. But no matter what, it's still just going to be the same idea that this energy has to be conserved. So for now, for today, the only ones we're going to worry about today are kinetic energy that's translational, okay? So in other words, it's just as the ball falls, we're not gonna worry about making the ball spin. And we're gonna worry about UG. And then we're gonna worry about KT prime, and we're gonna worry about UG prime. Eventually, we will work all four of these into problems. Today, it's just about translational, and it's just about UG, okay? So no us, no KR. We'll get to those, just not today. So here's the basic idea. Is that, imagine that I have a golf ball, which I do, and I hold it up to a height of 2 meters, and I'm gonna drop it, okay? So, when I hold it up here, what's the only type of energy that it has? Potential, right? Why does it not have any kinetic?
Because there's no velocity.
There's no velocity, okay? The only thing this has is UG. Now, as soon as I let go of it, what happens to that UG?
Turns into kinetic.
Changes into kinetic, right? Just like yesterday when I had the pendulum, and I lifted it up and I let go of it, it starts to swing down because Mother Nature likes kinetic more than potential. Okay. So, what we're going to do is we're going to set up a chart. So, here's the situation. I've got a ball. Let's say the mass is 0.1 kilograms. And let's say that that's 2 meters above the ground. And the sooner that you embrace this idea of setting up charts, the easier life is going to be. So in this situation, I'm going to have UG, I'm going to have KT, and then I'm going to have the sun, okay? So as you work through these problems, basically what we're going to do is we're going to keep track of what's happening to this energy through different stages of this process. So if you want to call this column the energy, okay? And for now, we're just going to have UG and KT. Eventually, we will have us. Eventually, we will have rotation, okay? Today, it's just UG and KT. That's it. That's all you have to worry about. So up there at the top, okay? So we're going to look at what's going to happen at the top. So up at the top, what's the only type of energy that I have? Because I'm just holding it.
Potential.
I just have UG, okay? I have no KT, if you want to think of this as being orange juice, okay? I have OJ. I have no kinetic energy because I'm just holding it. Now, if I throw it down, whole other story. If I throw it up, whole other story. If I throw it horizontally, whole other story, okay? But if I'm just holding it up there and I'm just going to drop it, I just have UG. Now, what I want to be able to do is calculate that UG. So what are the three things I need, Jack Ring, to calculate UG? How about a gravitational acceleration? Yeah. Rhymes with height. Height. Rhymes with brass. Mass.
Mass.
Okay. I had to be careful with that one what it rhymed with. Okay. So we got MGH, right? Now, what units is this going to be in?
Joules.
Joules. Oh, joules is the same thing as Newton meters, right? So if I take M times G, I get a force, right?
Right.
And I get a height that's in meters, so I get Newton meters, which is the same thing as joules. Ah, that's kind of clever, okay? So in this situation, I'm going to take 0.1 kilograms times G times the height of 2 meters. Now, actually, I'm going to change this up a little bit because it's going to make the math easier. I'm going to make the mass be 0.102. Okay, it's going to make the math work out just a little bit cleaner. So somebody take 0.102 times G times 2 meters.
Did I do it right?
What'd you?
She said, did I do it right?
2?
2 joules, okay? That's why I changed the mass to 0.102, because it's gonna make the math work out a little bit easier. So here's the story. So up there to the top, it has 2 joules of energy, okay? So what that means, and here's the absolute significance of this number. What that means is that that's the total amount of energy that I have in this system. That's it, okay? It can't be 2.04, it's not gonna be 1.96, it's gonna be 2 joules. So what that means is at any point from now on, the sum of all of these different types of energies can only be 2 joules. That's it, nothing else, okay? So this sigma down here means that's the sum of all the types of energy. So from here on out, no matter what happens, I have to make all of those energies add up to 2. Now, here's what I don't want you to think, like, oh, every problem is going to be 2 joules. No, okay? Because if I held it up only to a height of 1 meter, it would be a different value. If I held it up to a height of 10 meters, that would be a bigger value, okay? So don't think, oh, every energy problem adds up to 2. No, because like if I take Hank, right, and I take Hank and hold him up to 2 meters, that's a completely different amount of energy than if I have Gary the golf ball. Okay, so get out of your minds the idea that it's always going to be 2. It's just going to be a number, but the important concept is that the sum of these values is going to stay the same. Okay, so here's the deal. So I'm going to let go of it. And if you like the idea that this is a visual and you can look at this in terms of containers. So here's an UGG container and here's a KT. So my UGG container was initially filled up to the 2 joule line. Okay? That's how much UGG I have. My kinetic energy container is going to be empty. And we can transfer that energy from one to the other. So as soon as I let go of it, what's going to happen to the level in my UGG container?
Go down.
It's going to go
Down.
but my kinetic energy container is going to go up. Okay? So my kinetic energy is going to get filled up. That level is going to drop. This level is going to go up. Now, when it hits the ground, okay, when it hits the ground, how much UGG is it going to have?
0.
Why?
There's no height.
There's no height. So when this thing hits the ground, okay, I have no UGG because I have no height. So how much kinetic energy do I have then?
2 joules.
2 joules. Okay, right? So because the sum still has to add up to 2. Now, at this point, could I calculate the velocity of Gary the golf ball when Gary hits the ground? Mags. I know the kinetic energy.
Yes.
What would I do? Let me ask you this. Riddle me this, Batman. How do you calculate kinetic energy?
Half mass velocity squared.
Do you know the kinetic energy?
Yeah.
Do you know the mass?
Yeah.
What's the only thing you don't know?
Velocity.
So, you just told me, very profoundly, that kinetic energy equals 1/2 mv squared. Valid point, right? So, Ella, what does this equation look like solved for velocity?
V equals 2. Hold on. Remember, 2 kT
Yep,
over mass and
Yep.
the square root.
beautiful. Okay? Now I'm calculating velocity. True? Okay? So in this case, I'm going to take 2 times 2 joules divided by a mass of 0.102 kilograms. So let me know what you get. Don't forget to take the square root.
6.26
6.26
meters per second.
meters per second. Okay? That's how fast it's going when it hits the ground. Now, I want you to all to pretend that you know nothing about energy. Okay? You know nothing about energy. Your mind is a blank slate. And we are getting ready for the first big acceleration test. Okay? And I'm going to tell you that I'm going to drop a golf ball and it's going to fall a distance of 2 meters. And I want you to find the velocity of the impact. Okay? So you don't know anything about forces. You're just getting ready for the acceleration test. So you don't know time, but you know how far it falls. So, Topher, what equation am I going to use?
You don't know time, but you know distance.
This is true. I'm going to use that equation. So I have v squared equals v naught squared plus 2ad. True? Old school, right? Old school. Initial velocity is 0. V equals the square root of 2ad. So I'm going to take 2 times negative 9.8 meters per second squared times negative 2 meters because that's a displacement. And oddly enough, if you do the math, you are going to get 6.26 meters per second. Okay? You get the exact same answer. All right? And here's why. I can't have an energy part of physics going, oh, the velocity is 6.26 meters per second. And then have the kinematic equations going, oh, no, the velocity is 7.2 meters per second. It's like, whoa, 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 whoa. It's like, who do I trust? Do I trust the energy calculations? Do I trust the kinematic equations? So this is why I have to end up with the same answer. But now, what I want you to see is the difference. Okay? Here's what I want you to see is the difference. From the energy perspective, I had to have the mass. Okay? Mass side, the energy side, I had to have the mass. So here's the deal. Imagine this. Here I've got Hank, and here I've got Gary. Okay? I'm going to drop them both. Which one has more gravitational potential energy? Hank? Gary? Hank. Hank has a lot more mass, right? Okay? Hank has a lot more mass. So when they land, Hank's going to have a lot more kinetic energy than Gary is, right? But are they both going to land with the same velocity?
Yes.
Yes. Okay? So they're not going to land with the same energy, but they're going to land with the same velocity. And the difference is the mass. So I have to know the mass to do the energy side of the calculations. Okay? But I don't have to have the mass to do the kinematic equations. So whether it's Gary the golf ball, Hank an elephant, it doesn't make any difference. The velocity calculations aren't dependent upon mass. The energy calculations are dependent upon mass. But basically, the mass is going to drop out because if you think about what happens, like to get that MGH, that UG calculation, that was MGH. So I multiply by mass. But then when I do the velocity part of it, I divide by mass, so it basically drops out again. So that's why if I drop Gary, if I drop Hank, they end up with the same velocities, but they don't end up with the same energies. Okay? Got the difference between the two. Okay, now, man, that's heavy. Okay, now, here's the deal. So here's where we're at. When it was up here, it had 2 joules of UG. When it landed, it had 2 joules of KT. And the height was at 2 meters. So what I want to know is what's going to happen when Gary crosses the 1 meter mark. Okay? So now we're going to look at like something in between. So when Gary crosses the 1 meter mark, I want to know how much UG he has. I want to know how much KT he has. And I want to know how fast he's going when he crosses that 1 meter mark. Okay? So, which of those 3 do you think is going to be the easiest to calculate? The UG, the kinetic energy, or the velocity? UG. Why? What do you need to calculate UG? MGH. Right? Okay? kinetic energy is 1/2 mv squared. That's just going to be ugly. So, and again, here's what I want you to understand. Whether I hold Gary up to a height of 1 meter, or if Gary is falling and he passes through the height of 1 meter, doesn't make any difference. Okay, whether he's moving or not, as long as he's at that 1 meter mark, that's all that matters. Okay, that is all that matters. So here's the deal. So we can calculate UG, and that's going to be MGH. So somebody take 0.102 kilograms times G times 1 meter.
1.
Oh, you get exactly 1 joule. So, here's what we're going to do. We're going to go back up here to this chart, and we're going to add a third column about what happens when Gary crosses the 1 meter mark. So the UG is going to be 1 joule. Okay? In Gij, you get 1 joule. So how much kinetic energy does Gary have at that point?
1 joule.
1 joule. Because everything has to add up to 2 joules. Okay? It's kind of cool. All right. Now, let's talk about the velocity part of this. So, when Gary was up at the top, the initial velocity was 0 meters per second. When Gary landed, he was going 6.26 meters per second. Up at the top, he had 2 joules of UG. At the bottom, he had 2 joules of KT. At the middle, he has 1 joule of UG, and he has 1 joule of KT. So here's the million-dollar question. When Gary crosses the middle, so far here's the trend. Everything has been halves when he's at the middle. Half UG, half KT. So is the velocity also going to be a half then?
No.
Is the velocity going to be half of that, which is 3.13 meters per second? So you're going to have 3 options. Count them, studio audience. 3. Option A, the velocity is actually going to be bigger than 3.13 meters per second. Might be like 4, something like that. That's option A. Option B, it's just going to be exactly 3.13 meters per second because it's half, we've split everything else. Option C is going to be less than 3.13 meters per second because it's starting off slow and it's speeding up and it hasn't quite got to that point yet. Okay? So here's your options. It's going to be faster than 3.13, equal to 3.13, or less than 3.13. So how many think it's going to be option A, faster than 3.13 meters per second? Nikki B? Ella?
Yeah. Isn't there a square in there?
There is a square. So 3.
I got it.
Dime?
I feel like if
You're on the A train?
I feel like if Eli doesn't think it's right, it's not right.
You're on it? Zoe? You're on it? 5? Okay. How many think it's just going to be exactly 3.13? Nobody's on the B train. Less than 3.13. Okay. That's the vast majority. Okay? So, Sam, why do you think it's going to be less than 3.13?
It's gonna be less than 3.13 because it can't outweigh the actual energy of the equation.
It makes sense.
Hold on. Whoa.
The equation is 1/2.
Whoa.
The equation is 1/2.
You can't outweigh the energy.
It has.
Yeah, the velocity count with it.
Have you ever heard Grease so much in class?
Is that alright? It has 2 joules.
Okay, unleaded. Okay,
Unleaded, you missed it.
Unleaded.
Right? It has 2 joules of energy. It's
I think you're a little
equation. It can't.
I think he's
hold on,
unleaded.
Sam, articulate that a little bit more.
So like velocity in the equation is v squared, right?
Yeah.
So it has to be 1/4.
So you're thinking it has to be 1/4.
It's 1/4, yeah.
Okay, all right. Okay, because it's like half and that's v squared, so it's got, okay, all right.
Exactly. See,
So how can we settle the argument?
Calculate.
Brawl.
A brawl. Brawl. Okay, physics brawl. Huh. Chuck to look. Okay.
You want me to?
Now, just up the road a little bit, we said we can do this to calculate velocity. True?
True.
Okay.
Oh,
Uh-oh.
no.
You said uh-oh.
Keep going.
So we're going to take 2 times 1 joule and divide that by 0.102 kilograms.
Oh yeah, it's definitely less. 100%.
It's not.
How much do you want to bet?
10% of your grade.
I don't bet nothing. Keep going.
How much do you want to bet?
Keep going.
How much do you want to bet?
No, I won't bet anything.
Come on.
The bet measure.
Come on, Mr. Confidence.
I'll bet Jack's life on it.
What'd you get?
Lost a lot.
4.43.
4.43.
See, I said more.
No, you didn't. That's a bold-faced lie.
Like in my head. I
No, in your head you said that. Okay, yeah, tell that to the bookie when he comes to like collect on your betting debt. Okay, in my mind I meant to bet on the Cowboys, but I didn't. Okay, so here's the deal. It's very much bigger than that,
Yeah.
okay? Why? Because math.
Because
Okay.
of the mass.
Now let's look at this. Let's just step back for just a second. Does velocity change as a linear function of distance, or does velocity change as a linear function of time?
Time.
Time, right? Which is why velocity time graphs have, that's time, have a straight sloping line, right?
What's the other one?
So here's the question. What takes longer to fall? The first meter or the second meter? When is the ball in the air longer?
First meter.
The first meter or the second meter?
First.
So the ball takes longer to travel the first meter than it does for the
Oh, yeah, yeah.
second meter. So gravity has more time to act on it
Yeah.
in the first meter. And so because velocity changes as a linear function of time, that's why it's going faster in that first, at the end of that first meter. Mickey P's all hyped now. Okay? Okay? Stick it. Okay? And that's why it's going faster, because it doesn't take as long to fall the second meter as it does to fall the first meter.
Yeah.
Like, you like that, Sam?
Yeah. See, I was thinking of like a different meter, so.
Okay,
Yeah.
we got it?
A parking meter.
Okay.
I was thinking of like the imaginary numbers, you know.
Huh?
What?
Geometry.
No. Okay. Got that.
Yes,
Okay.
sir.
So now I want to change it up. So, Sam, pick a number between 20 and 30.
29.
God, you picked a prime number. All right. If this math is ugly, it's because of Sam.
We can do a different number.
Nope. Die's already cast.
Sorry.
Hey, can I borrow Topher for a second for yearbook?
Yeah, as long as you don't bring him back.
Alright.
Cool.
Oh, she has
very
such a nice
popular.
voice.
It's gonna be about the world.
He seems like a nice person.
Can we put the World Cup on? And she wish you had done it.
Yeah.
Oh my gosh, we need to ask her fourth block.
People only make fun of mine.
Okay. So now I want to change it up.
That's a one.
The game?
Yes.
Yeah. Hey, U.S. plays Iran at 1 p.m.
Okay.
What?
Okay, I don't get Fox, so.
I have Hulu.
It's Iran.
We can pull it up.
You can do it in
I
fourth
was
block.
watching it during
Fourth
Encore.
block. Jack, fourth block.
Have you seen that joke? It's like, how do I get out of Iraq? Iran.
Let's go.
Yeah, I've heard that too.
Sorry.
That was kind of funny.
Okay, anyway. So, we'll take the ball, now we're gonna reverse the process. Now, because someone picked a prime number, we're gonna throw the ball up in the air at 29 meters per second. Okay, so we're gonna establish the ground as being like the reference point. Okay, so we're gonna throw this up in the air at 29 meters per second. So it's the reverse process. So at the bottom, what's the only type of energy that it's gonna have? Kinetic. So as it goes up, what's going to happen to the kinetic energy? It's going to change into potential. At the top, all of the potential energy, all the kinetic energy is going to be
Zero. Potential.
potential.
Yeah.
Right? All the kinetic energy is going to be potential. Why will it not have any kinetic energy at the top?
Because no motion.
There's no velocity. Why?
Max height. It switches direction so it reaches zero velocity.
There you go. Because
Yeah.
it's got to slow down, stop, and
Speed back up.
Okay, so we can calculate how much kinetic energy that we have.
No.
So we can go 1/2 the mass of 0.102 kilograms times 29.0 meters per second squared.
Yeah.
Yeah, this is just going to be so ugly.
That was mine.
Okay, what do you get?
Oh. I don't know.
It's going to be a big number.
42.9.
42.9
I agree.
Still,
I second that.
joules. Okay, so about 43 joules, right? Okay, so what we're going to do now is we're going to set up a chart. And the sooner you embrace this idea of charts, the better off you're going to be. So we can have UG, we can have KT, we can have the sum. So at the bottom, we have no UG. We've got 42.9 joules of kinetic energy, so that means the sum has to be,
42.9 joules.
so now that's the magic number. So this is why if you ever double check a calculation, you double check that you did this calculation right. Because if this number is wrong on that pure form of energy, whether it's UG, whether it's kinetic, doesn't make any difference. If this number is wrong, everything else is going to be wrong. Okay? So make sure that you do that calculation right, because literally everything you do is going to be jacked up from there on out. Okay. So I got 42.9 joules of energy. So when I get up to the top, right, how much UG am I going to have?
42.9.
42.9 joules. How much kinetic energy am I going to have?
0 joules.
0. So that means everything has to add up to,
42.9 joules.
okay? So now how can I use that dime to find my height?
You could split even. Wait. Oh no, sorry.
Split even.
No, I'm thinking I was thinking back at the 1 meter thing.
Yeah.
Between.
Yeah.
So MGH.
Ah! So UG, what was the guy in Frozen, the lumber guy?
Christoph.
Christoph, yeah, you kind of got that look, don't you?
Aw.
That's a Norway, so thank you.
Yeah, okay, yeah. I like to go T-Rub, that was nice.
Go see the-
Yeah.
I-
All right, so Christoph, okay,
Oh god.
Christoph
It just
died.
reminded me of something, but I can't put my
So, how am I gonna get H by itself?
You will divide UG by MD.
UG by MG equals H So somebody take 42.9 joules and divide that by 0.102 kilograms times,
9.80 meters per second squared.
thank you. Like I hear this voice in my head going, 9.8.
42.
What'd you get?
Oh, dear.
42.
Do you really?
See, it works out perfect. I do that in the
I
store.
mean, with 3 significant digits,
Yeah.
yeah.
42.0?
Yeah.
That's nice. Okay.
You're welcome.
Great numbers.
Now, what would happen to that maximum height, okay,
Are you sure?
if I launched Hank at 29 meters per second? What would happen to the value of that maximum height? Be less? Why would it be less?
Dividing by a bigger mass.
Oh, I'm at 43.
Oh, yeah.
It's still 42.9.
Oops, I forgot the 0.9.
That's my
Yeah,
bad.
it's messed
42.9.
That's my bad, sorry. It's 42.9,
It's
sorry.
okay, guys.
It was going to be so nice.
Sorry, I just wanted it to work
It's
out.
the same as the
That's
energy.
my bad guess.
Because it's like dividing it by 1.
Oh,
Yeah, because then it's like dividing it by
that makes sense.
I just wanted it to work out.
I
Sorry.
know. Okay.
That's on me.
All right, so let's go back to the idea of if I launched Hank with the exact same velocity of 29 meters per second, would that maximum height, the 42.9,
Yeah.
be bigger, smaller, or still 42.9?
If you launched it
Smaller.
from.
So Sam, so how many think it's going to be smaller?
Wait, what's the question?
Is the
Smaller.
maximum height going to be bigger, smaller, or equal to 42.9? So how many think it's going to be smaller?
With a larger velocity?
No, exact same velocity of 29 meters per second.
So what's changing?
My,
Oh, the mass.
I'm going to launch Hank at 29 meters per second.
Oh, small.
So
The
is the height
velocity?
going to be bigger?
The height? Sorry?
Are we good?
Yeah.
So how many think the height is going to be less than 42.9? How many think it's going to be greater than
No.
42.9?
Rella, lower your hand.
How many thinks it's going to be equal to
Rella, lower
42.9?
your hand.
Is it not?
Rella.
I have failed
Oh.
all of you as a teacher.
I thought it's
For
the
the
same.
love of God,
Is it the same?
look, what if you use the kinematic equation of v squared equals v naught squared plus 2ab?
So I was right?
Yes!
Yes! I know, that's why I was like, guys, literally mass does not have an effect on it.
Yes, but it also is going to have more kinetic
Right
energy.
here.
Oh, yeah.
Me and Gracie were right.
Gracie did
Yeah. Oh, I guess. What can I say?
I just like looking like, oh, that's something.
So, but it's going to have more kinetic energy at the beginning because it has more mass, right? So there's going to be more energy in the system.
God.
So when it gets to the top, it's also going to have more energy, right?
Once again.
But then, once again, in your head,
Yep.
that's what you were thinking.
That's what I was thinking. It's just not what I said.
Okay, all right.
Please get this.
I don't recommend you go running for politics. Okay? I was thinking that, but I said that. Really? Okay. So, the height is going to be the exact same. Because look, if you go to the old school kinematic equations,
Period. Period.
what?
Point blank period, you know? I know, but like, that's like, I was like, that doesn't make sense. Mass doesn't have a, you know?
Okay. So, if you go old school, the mass doesn't matter. Whether it's Gary, an elephant, or Drebin, okay? If you launch that thing at 29 meters per second, you're still going to get the exact same height of 42.9 meters because the mass doesn't matter.
Nice. So what changes then? Kinetic energy.
Okay.
Yeah, because you have a greater kinetic energy. With a greater.
Okay. That's a lot of energy going on, girl. Okay. If we're going to harness that energy,
I
we
ran
can
on
power
the
the
treadmill and I was
whole
thinking, am I powered
Okay.
by the Y right now?
Got that
I
idea.
do that
Now,
yesterday.
let's say let's say, that I take a rubber band and I stretch it. Am I doing work?
Yes.
Why?
Well, I think so.
I'm exerting force over a
Distance.
distance, right?
Yeah.
Cool. So as soon as I let go of it, what's going to happen to that potential energy?
It's kinetic.
It'll change into kinetic energy, right? Now, what if I launch that rubber band straight up? So what would be the relationship between the potential energy that I store here, the kinetic energy that it has when it leaves my thumb, and the gravitational potential energy it would have at the top?
The
Potential
kinetic.
to kinetic back to potential.
They're all
The
They're
sum.
all the same.
Yeah.
Yeah.
Wait, what?
They'd all be the same, right?
Oh, yeah.
Because
One
the
zero,
work
one
that I
wild
do
you know?
in stretching this,
1 0
true,
wild ones.
Yeah.
That, you know?
is going to change into
Oh,
kinetic
Stay with
energy
those two.
Yeah.
here, which is going to change into
Potential.
potential energy at the top. So then you'd have like a 3-container system. You'd have energy stored in the rubber band,
Yeah.
okay? Oh. Let's look off my- There it goes. Okay.
Hi, Leslie.
Now, if I shot it horizontally, okay, it would go up like
I was
that.
gonna give you help, but then I got in trouble
But
for
here's the
being on my
idea,
phone.
the energy's going to stay the same. Now, when it changes up the system, what if I go back to Gary the golf ball, and I want you to think this through. And what we've talked about so far is I dropped Gary, right? Okay? What if I throw Gary up in the air? Then, what's going to happen to the velocity that Gary has when he hits the ground? Here I drop Gary. Here I throw Gary.
He's gonna have a greater velocity when you throw it.
Why?
Because when you throw it, it's gonna go to a greater height, and then it'll have a greater distance from the top max height to the ground, which means gravity can act on it for longer. And gravity's acceleration, I mean.
That's a beautiful old school equation.
Yeah.
Or explanation.
Oh, okay.
Oh,
I agree, but it confused me some.
okay. Hold on. So,
It's like the
What-
problems
what
when they
Morella
go off the
was
cliff,
saying
but they throw
is
it.
that if I throw it up in the air, right, versus just dropping it. So, if you look at v squared equals v naught squared plus 2ad, right? If I just drop it, what's my initial velocity?
0.
0. So that's just going to be 2ad. If I throw it, then my v naught value is not
0.
0. Okay? So that means I'm going to have a bigger number on the right, so it's going to land with more velocity, because it's going to be, in effect, falling from a greater height when it hits the ground. Now, let's look at it from an energy perspective. If I just drop it, what's the only type of energy that it has at the top?
Gravitational potential energy.
Right? It's the only thing I have is
Yeah.
And all that changes into kinetic at the bottom. True?
See.
True. But if I throw it, what 2 types of energy does it have?
Kinetic
Kinetic
energy and
and-
gravitation.
Oh, so if I throw it, it has KT and right?
Right.
But when it lands, it only has
KT.
KT. True?
Yeah.
Makes sense.
That's gonna be big.
So I'm going to call this KT naught. Okay, that's the initial amount of kinetic energy. True? Okay. Now, what if I throw the ball down?
Oh, then it's gonna have KT and.
Oh, no.
Uh-oh.
Okay. I throw the ball up with a certain velocity. It's going to land with a certain velocity, right? If I throw the ball down, as opposed to throwing it up, so if I could throw it up at 10 meters per second or throw it down at 10 meters per second, will that impact the velocity when it lands? If I throw it up or if I throw it down, both at 10 meters per second?
Yes.
You sure?
Oh, no.
I mean, I think so. It doesn't?
Sam, I'm going to give you a chance to completely make sure that what comes out of your mouth is what
It's
you were
exactly
thinking.
what I'm thinking. Okay.
So, here's the question.
Okay.
I want to make sure everybody's cool with this scenario. Scenario number 1, I throw it down at 10 meters per second.
Yeah.
Okay? Scenario number 2, I throw it up at 10 meters per second.
Yeah.
Question being is that when it hits the ground, is there a difference in the velocities whether I throw it or if I throw it down or if I throw it up?
No, because the KT and the UG will be the same.
Oh, beautiful. Now is that really what you want to say?
That was what I was thinking.
You sure?
Wait,
Yeah,
why?
that's
Okay,
how I
good,
was
because
thinking.
that's right. Because look, is kinetic energy a scalar quantity or a vector quantity?
Scalar.
Because it's 1/2 mv squared, right? So the direction that I throw the ball up or down, does that matter?
No.
No. If I have negative velocity, it's still going to get squared. If I have positive velocity, it's still going to get squared, right?
Right.
There's an interesting idea. What if I throw it at 10 meters per second, but I throw it at an angle?
It doesn't matter.
Doesn't.
Why doesn't it matter?
Because it just stays in the, the axis is.
Whoa.
What?
I thought like
You're making this complicated.
the velocity
Why are you
of the
making
x
this
doesn't matter.
No, it does.
Oh,
okay?
it does?
It does. But not in this case.
Oh.
So here's the
Wait,
deal.
what?
So, is there any way to plug into that 1/2 mv squared the fact that I threw it at a 45-degree angle?
No.
The angle doesn't matter. So here's the cool thing. If I throw it up, if I throw it down, if I throw it at an angle, if I throw it horizontally, doesn't make any difference. As long as I throw it with the same velocity, it's still going to have the same amount of initial kinetic energy. Okay? Okay. So it doesn't matter. It's all going to be the same. Now, here's where the magic happens. Woo. Woo. Does everybody agree that that initial kinetic energy is going to be 1/2 m v naught squared?
Yes.
Everybody cool with that?
Yeah.
And UG is going to be mgh?
Yeah.
Everybody cool with that? My final kinetic energy is going to be 1/2 m v squared.
Yeah.
Cool with this? I hate fractions, so how can I get rid of the fractions?
Everything by 2.
Multiply everything by 2. So I get mv naught squared plus 2 mgh equals mv squared. What can I get rid of?
Wait.
No way.
Wow.
No way.
Hold up.
What do you get? That equation.
Equation.
You get that equation.
Yo.
So that equation comes from the law of conservation of energy.
Oh.
I'm not
Okay.
trying to do that.
That's where that comes from. Now, interesting thing happens. If I just drop it, what happens to V naught? 0. So 2gh, that's just your potential energy part. The V squared is your kinetic energy part. And if I throw it, then I have V naught squared. So that tells me, oh, that's the initial kinetic energy that I have. So that equation comes from the law of conservation of energy. Okay?
Wait. So that equation comes from this equation. Oh.
Ah,
Is that how they,
like that?
Did the name?
Like that? Okay, stop that camera.
Okay.
Okay, so number 1 involves a guy by the name of Suave Bronco. That happened many, many years ago. A kid was reading some random book, and he goes, Burkamp, here's the challenge. Incorporate the name Suave Bronco into a problem. I said, I got this. So that's where Suave Bronco came from many years ago. When you get to number 4, okay, so on number 4, here's the setup. So imagine this is like an archer on a much smaller scale. So this is what we talked about in the sense that I'm going to take this rubber band and I'm going to stretch it like this, okay? So I'm going to exert a force of 201 newtons over a distance of 1.3 meters. So imagine this. I'm going to stretch this, okay? I'm going to pull this thing back. Am I going to do work?
Yes.
Because I'm exerting a force over a distance. So when you sketch this graph on 4A, here's what that needs to look like. You're going to exert a force of 201 newtons over a distance of 1.3 meters. Now, what is the area underneath that line going to give you?
Work.
Work.
Don't get the first one.
Then, that work is going to be stored as energy. So as soon as you let go of it, what's going to happen to that energy stored in the bow? It's going to change into kinetic energy, and then that kinetic energy is going to change into at the top. Okay? So on number 4, all you're doing is changing types of energy. Now, when you get to questions, or letter E on number 4, what physical quantity is given by the slope of a momentum time graph? Got to go old school, okay? I'm not asking you to draw the graph. I'm just asking you to look at what the slope's going to represent. And then, knowing that, what I'm asking on 4F is that if you have a momentum time graph that has any kind of straight sloping line, what has to happen for you to have a sloping line on a momentum time graph? Okay? Got to kind of go old school, back to momentum, and think that one through. When you get to question number 7, so here's a rocket, and we're going to launch this thing up from Cape Canaveral. I've given you the net force of 3.89 times 10 to the third. Accept it as a gift, okay? You don't have to calculate the net force. That is the net force, okay? That is the net force. When you do work equals force times distance, that's the force that you're going to use. You don't have to subtract out the weight and all that other jazz, okay? Accept it. It's a gift. Do not make it complicated, okay? Do not make it complicated. When you get to number 8, you've got to go old school momentum, okay? So on number 8, imagine these people are facing each other. They're going to push off. What's the initial momentum of the system? 0. So afterwards, what does the momentum have to add up to? 0. Keep that in mind. Okay, I'm done. You're on your own.
Bye, Leslie.